When we start talking about graphing logarithmic functions, we really need to see what the similarities and differences are between it and its inverse function, which is the exponential function. And any exponential function is the inverse of the log function that has the same base. So just as an exponential function can have different bases, but it's still an exponential function, you can have log functions that have different bases, and they will be inverses of one another because they have the same base, these two equations. So let's look at these two on a graph. We know that this is going to be a growth, an exponential growth type thing, and if you recall, our points were, it always went through the point 0, 1 until we transform it some kind of way, but the parent function always went through 0, 1. And then on the left side, it went through at -1, 1/2. And on the right side, it went 1, 2. And then it went 2, 4. And then it went 3, 8. And that's about all we could fit on these graphs. And so if you recall, y equals 0 is that asymptote that kind of is that imaginary line that runs through along the x-axis, and it's horizontal, so it's a horizontal line, and it's called y equals, not x equals. So y equals 0 is that horizontal line. So this graph, it'll keep getting closer and closer to the x-axis, but it will never cross or touch the x-axis. And so it will look something like that. It's always hard to show the left end because it's just getting closer and closer to 0, and it's hard to show that with a hand drawing. So that is our function. Let's put maybe a little dotted line here to show you this is where that y equals 0 asymptote is, and that's what it looks like. It does keep getting wider and wider up here. It is not going to come across an asymptote. It's just going to keep getting wider and wider on that end, but it does have an asymptote underneath it, a horizontal asymptote. So in order to easily graph the log base 2 of x function, what we want to do is look at the ordered pairs, some of the ordered pairs that we made in the blue graph. What you want to do in an inverse function is you literally flip-flop the x and the y in the point. So our new points are going to be the inverse of those points, which means just swap spots. So we're going to take 1/2, -1. We're going to do 1, 0. We're going to do 2, 1, and 4, 2. And we'll just start with those. So we're going to graph these points. So inverse functions will always have their x's and the y's flip-flopped. So 1/2, -1 would be about right here. And then 1, 0 would be right here. And all parent functions of log functions will have their point going through 1, 0, just like all the parent functions, whether they were growth or decay, their original functions always went through 0, 1 on exponential functions. Well, log functions are now always going to go through 1, 0. Then we have 2, 1, and we have 4, 2. And eventually we'd have an 8, 3 out there, just like we had a 3, 8 on the other one. And so what happens here is, let me get that green line again, there ends up being an asymptote going the other direction, perpendicular to the other asymptote. And that is a vertical line, and that vertical line is called x equals 0. So its asymptote, log functions in their parent function position have an asymptote of x equals 0. So therefore, if we go back and graph this, we just know that it can't ever cross over that line, no matter how bad we want to put it over there. We need to keep it on this side of the green line, and then this will go up and keep getting higher and higher, but also keep getting more and more right. So that's what the inverse function of the exponential function looks like. And the red one is called the log function at base 2. The blue one is called an exponential function with a base of 2. Something that you may have seen before is that anything and its inverse function will always be a reflection of one another. And they're not a reflection over the x-axis or a reflection over the y-axis. They're actually a reflection along the diagonal line that would separate this quadrant or this graph kind of right down the middle, and come down here and do this. This slanted line is called y equals x. And that slanted line is going to be the line of reflection between something and its inverse function. So something and its inverse function will always be a reflection over the y equals x line. And that's not just with logs, that's with anything. Something and its inverse function will always be a reflection of the other. And specifically a reflection over the y equals x line, which is basically a line with a slope of 1, that's that purple line there. As we learned in exponential functions, when the b or the base is a number between 0 and 1, then this will be decay rather than growth, which means from left to right it will be going in a downward pattern. And so let's plot some points that I've gotten off this table. So -1, 2 is right here. Then we have 0, 1, which both growth and decay parent functions will go through 0, 1. Then we have 1, 1/2. And then we have 2 goes down to 1/4. And what's happening here is we're going to get closer and closer and closer to 0, but never touch it because there's an asymptote there as well. So this graph is going to be going up and then getting closer and closer and closer to the x-axis in that way. So that is a decay function, or an exponential function of decay. And then if we have the same base but as a log, then log of x with a base of 1/2 is going to be a reflection of that as well. This reflection is a little harder to see, but it'll be easier if we just write the ordered pairs reversed of what we see here. So if this is -1, 2, we do 2, -1, then we just reverse them all. And then let's see where those look like they are. 2, -1 is here. Then we have 1, 0. Then we have 1/2 to the side and 1 up, so that's about right here. And then we have 1/4 to the side and 2 up, so that's getting closer and closer to the y-axis. And it's going to do, there's an asymptote at the y-axis, and then it's going to do something like this. Just like any exponential function, the blue function will have its asymptote along the x-axis, which is actually called the line y equals 0. And then the log functions, like every parent log function, will have its asymptote along the y-axis, which is actually the vertical line called x equals 0. Then in addition to that, we've got this reflection line that we talked about. So every inverse function will be a reflection of its original function over this slanted line that goes through right, kind of cuts right through the center of all those squares. I'm not making it super accurate here, but and so let's see how this is a reflection. Take a point over here, and you go straight across the same distance, and you've got a point on the blue line. So you always want to go straight across in a perpendicular direction to the line of reflection. This reflection line is the line y equals x. We talked about that. And every point in blue should reflect across that line in red. So if we take this point, reflect it straight across, we get this point. If we take this point here and reflect it straight across, we get this point here. And so you can see every point on the blue is actually a reflection of a point on the red. And so like we could take this one over here, reflect it straight across, and we're getting this point over here, something like that. So I couldn't draw it perfect, but we're pretty close to seeing that reflection. So those are some properties about exponential functions versus log functions. The last thing I want to talk about on these graphs are the domain and range. On the blue graph, the domain is left to right, range is bottom to top. I used Oh Lord the Robot as a little saying to remember how those work. So the domain of the blue exponential function is everything from the left boundary to the right boundary. Well, the left boundary is negative infinity. It goes on forever to the left. The right boundary, this is going to not only go up, but it's going to continue getting wider and wider, and so it is going to also go to the infinity to the right. Then, if they ask for it as a set of x's, left to right, you would say x can be any real number. Then, the range. The range is bottom to top, so we look at our bottom of our graph and the top of our graph and say, what's our range here? Well, it never goes lower than the x-axis, which is the y equals 0 line, and so you could say y always has to be greater than 0. It's not greater than or equal to because it doesn't touch the x-axis. It's just going to get closer and closer to it. Then the range from bottom, you would say 0, and then top, it goes up forever, so it's positive infinity. That is your range. The red log graph has a domain left to right. There's a left boundary at 0 because it never goes to the left of where the y-axis is, but it does go to the right forever. And then the range, by the way, we would say that's x, everything greater than 0, if you had to write it in that notation. It just depends if they ask for interval notation or set notation. And then the range is the bottom is forever down, so negative infinity. The top is going to be forever up. Yes, it goes forever to the right, but it constantly is going up as well. Just it rises little by little. And the last thing I want you to notice, so that would be all real numbers as far as what y can be. The last thing I want you to notice is that since they're inverse functions, the domain of one is the range of the other. The domain of one is the range of the other. Those should match all the time when you're doing inverse functions like this.